Hi, I'm Nikhil, and I will be talking about fine-grained lower bounds for approximately solving linear equations. This is joint work with Mitali Bafna. What exactly do we mean by approximately solving linear equations? We will consider the following definition. We are given a satisfiable linear system A, B, that is, there exists an x such that ax equals to b, and we just want to find an approximate solution y such that the norm of ay minus b is less than epsilon times norm of b. Note that epsilon equals to 1 is trivial by just taking y to be the all zeros vector, and epsilon equals to 0 corresponds to exactly solving the linear system. You might be aware of stronger notions of approximation, which are defined for all linear systems, not just satisfiable ones. These notions reduce to this notion when we restrict our attention to satisfiable linear systems. As we will concern ourselves with giving hardness for this easier notion of approximation, the hardness will also apply for more general notions. So what are the known algorithms for approximate linear search problem? The best known algorithm is the same as the one for exactly solving linear equations, which runs in time n to the omega, where omega is the matrix multiplication constant. There are two papers mentioned above as they give algorithms for exactly solving linear systems over real RAM and word RAM respectively. Our reduction works for both models, and I will not be differentiating them for the purposes of this presentation. For restricted linear systems, Spielman and Tang gave near linear time algorithms for specific classes of linear systems such as Laplacian linear systems. This result was then built upon by many works to give algorithms for other restricted classes of linear systems such as directed Laplacians. Our main result. So a natural question here is that till how far can these techniques be extended? Could we hope to get improved algorithms for general linear systems, not just restricted ones? Our main result is that approximately solving linear equations is conditionally hard for running time n to the omega, which matches the known upper bounds. And we proved this hardness for epsilon equals 1 minus 1 by n. Remember that epsilon equals to 1 is trivial, and we proved that doing marginally better than that is conditionally hard. We also extend this result for restricted classes of linear systems, such as sparse linear systems, where the number of non-zero entries is O of n. Here we are able to give omega n square hardness. For linear systems where the matrix is a PSD matrix, for linear systems where the condition number is bounded above by poly n, and finally for approximately solving linear systems with respect to the LP norm instead of just the L2 norm for all p greater than or equals to 1. For all these results, the exact conjectures under which we give hardness are slightly different, and I will mention some of them a bit later. Some implications of our results. There are other works which assume the hardness of approximately solving linear equations and reduce them to other problems. These works can be directly composed with our reduction as we give the conditional hardness for approximately solving general linear systems. For example, composing with the prior work of King and Zhang, we get the hardness of approximately solving restricted linear systems such as multi-commodity Laplacians and total variation matrices. Similarly, composing with the work of King, Wang, and Zhang, we get hardness for packing and covering linear programs. One way of interpreting our results is that the Spielman-Tang kind of algorithms cannot be extended conditionally to general linear systems. So what is the hardness of our main result based upon? The hardness of our main result is based on the rank finding problem. which just asks given a matrix to find its rank. The best algorithm for this problem also runs in time n to the omega, and we conjecture that this is optimal. I mentioned earlier that we prove extensions of our results for restricted classes. For these extensions, we prove the hardness under modifications of this conjecture. For example, for sparse linear systems, we prove hardness under the hardness of rank finding problem for sparse matrices. So what is the evidence in support of our conjecture? Well, firstly, the related problem of computing the determinant is provably as hard as matrix multiplication, but in the model of arithmetic circuits. Current approaches, which attack similar problems as to computing the rank, fail to even approximate the rank of a matrix, let alone determine it. And finally, falsifying the conjecture, that is, giving a faster algorithm for the rank problem, would improve various graph algorithms such as finding a perfect matching in a graph, which are well studied in their own right. Now let's just do a proof sketch for our main result, which is that approximate linear search problem for general linear systems is n to the omega hard for epsilon equals 1 minus 1 by n. Let us start with introducing the decision version of approximately solving linear systems. We call this the epsilon approximate linear decision problem, epsilon ALD for short. In the decision version, we only have to distinguish between the yes case, where the linear system is satisfiable, and the no case, where every solution has error at least epsilon times norm of p. We proved that the hardness for this problem implies hardness for our original problem of approximately solving linear systems using a decision to search reduction. I won't go through the proof of this. I'll just mention that this is not the direct usual sort of decision to search reduction. And we are able to prove this reduction using the fact that the decision problem is a gap problem. Now let us, with this definition in hand, let us look at the overall plan for the reduction. We will first reduce the rank finding problem to the full rank problem. This reduction was already present more or less in prior work. Next, we will reduce the full rank problem to the approximate linear decision problem with epsilon equals to 1 by n square. And finally, we will amplify the gap, that is epsilon, from 1 by n square to 1 minus 1 by n. Let us first look at the reduction from rank finding to the full rank problem. So the full rank problem just asks, given a square matrix, to distinguish between the yes case, which is when the rank is n, and the no case when the rank is less than n. As I mentioned, this reduction was already present in the prior work of Weidman, who did this reduction for finite fields, and we just do it over reals and rationals. So I won't go over it. Now let's look at the reduction from the full rank problem to the approximate linear decision problem with epsilon equals to 1 by n square. Let A be our matrix in the full rank problem. That is, in the yes case, rank of A is n, and in the no case, rank of A is less than n. We'll sample a random Gaussian vector B, and our resulting linear system will just be A comma B. So this completes the reduction. Now let's argue correctness. In the yes case, rank of A is n, hence there exists an x such that Ax equals to B. So the linear system is satisfiable. In the no case, rank of A is less than equals to n minus 1. This implies that there exists a unit vector which is orthogonal to all columns of A. That is, W transpose A is the all zeros vector. Further, as B is a random Gaussian vector, we can argue with high probability that W transpose B is greater than the norm of B divided by n square. This is sort of a kind of an anti-concentration result, basically. Finally, together these imply that the norm of Ax minus B is greater than the norm of b divided by n square. And this completes our reduction because we are able to say that in the yes case, the linear system is satisfiable, and in no case, for all solutions, we at least have norm b by n square error. Now we will amplify the gap, that is epsilon, from 1 by n square to 1 minus 1 by n. Let A, comma the all ones vector be our initial linear system for the 1 by n square approximate linear decision problem. Note that the target vector now is the all ones vector. And this can be done without too much loss in epsilon, so I will be skipping this step. Let our linear system be as follows. A1 transpose x equals to 1, A2 transpose x equals to 1, and so on till AN transpose x equals to 1. We will transfer our linear system as follows. Our new set of linear equations will be of the form t plus 1 times A1 transpose x minus t times A2 transpose x equals to 1, and so on cyclically. And we will take t to be n to the power of 4. This can be thought of as pre-multiplying the whole linear system by the following matrix M. This gives us the new linear system mx equals to m times the all ones vector, which turns out to be just the all ones vector. The operation of matrix M on a vector amplifies all the components orthogonal to the all ones vector while not modifying the components along the all ones vector. This allows us to argue that our target vector, which is the all ones vector, remains the same while error gets amplified. I won't formally prove this, but you can go through the paper for the formal proof of this fact. This completes our reduction. Now let's go through some other properties of the reduction which are helpful in proving some of the extensions. The first is that we preserve the number of equations. This allows us to conclude that the final linear system for which we will give hardness for will have a square matrix. Secondly, since M has full rank, we can argue that in the yes case, the matrix of our linear system will have full rank. So these two properties are extra properties that we can promise in the hard instance, in the instance for which we give hardness. Thirdly, as the matrix M is sparse, the sparsity of the linear system increases only by a constant factor. This allows us to argue for the hardness of sparse linear systems, which was one of our extensions. And finally, a point about why we needed to do the reduction in this specific way, which is to first increase the gap to 1 by n square, and then finally to amplify the gap to 1 minus 1 by n. There exist linear systems, a comma b, with exponentially small gap. That is, for all x, norm of ax minus b, for all x, ax is not equals to b, but there exists x such that norm of ax minus b is less than the norm of b divided by 2 to the power of n. For such linear systems, to amplify the gap, we would need to take t equals to 2 to the omega of n, which would have blown up the complexity of the matrix entries. We can only take t equals to n to the 4 as we are already promised a gap of 1 by n square from the earlier part of the reduction. So this completes our discussion about the reduction. Let's move to some future directions. So our reductions go through the approximate linear decision problem. Can we give a direct search to search reduction? That is, from exactly solving linear equations to approximately solving them? In fact, the second step of our reduction is such a search to search reduction. But we don't know how to modify the first part of our reduction to give a search to search reduction. So this is the part where we reduce to epsilon equals to 1 by n square. Conjugate gradient descent has a square root of condition number factor in its running time. Can we prove that this factor is optimal under some fine-grained assumption? And finally, for the hardness of well-conditioned linear systems, our hardness is based on the problem of checking whether a given matrix is full rank or not, with the extra promise that in the yes case, the matrix will be well conditioned. This problem seemed natural to us but has not been studied much. So, can we base the hardness on a more well studied problem? Thanks for listening.